Hi, I'm going to attempt a quick introduction into electromagnetic radiation. I encourage you to go back and look in the textbook and just make sure you understand some of the finer points, but I want to go through just roughly what you need to know about the nature of electromagnetic radiation. So, first of all, one of the things you're responsible to know is the types of electromagnetic radiation and really have to know, um, I guess, the order of the electromagnetic spectrum and should know kind of the relative um, wavelengths and frequencies for each of the parts of the electromagnetic spectrum. And so I'm going to do a real quick overview of that. You'll have to go back and take a look. Just clean this up. Wavelength and frequency. Um, yeah, so you'll see a lot of charts that kind of lay out the electromagnetic spectrum in lots of different visual ways. This one's no different. And in this case, we're going to go from uh, low frequency to high frequency. So on this side of the chart, you have low frequency. Up here, we have high frequency. So one of the things we're going to see is that electromagnetic radiation is defined by its frequency. On the flip side, we can also talk about wavelength. So up here, you see the different frequencies. Down here, you will see the wavelength. And kind of is an inverse relationship. On this end of the spectrum, we have long wavelengths. On this end of the spectrum, we have short wavelengths. So we're going to try and keep track of this as we go. We'll have a chance to revisit it again. No replacement for going back and just kind of studying up from your textbook or from these notes. So let's start. First of all, you need to know the order and the categories of the electromagnetic spectrum. Most people have heard of most of these. We got radio waves as being the things with the lowest frequency and the longest wavelengths. Then we move up in frequency to microwaves with their higher frequency, a bit shorter wavelength. Then we have infrared. Then we have probably in our day-to-day life the most important part of the electromagnetic spectrum, that's visible light. Then if we go into higher frequencies yet, we get ultraviolet, X-rays, and finally gamma rays. So these are the 7 different parts of the electromagnetic spectrum that you should be familiar with. You should know them by name, and you should know the order of them, and should know kind of the relative wavelength or frequency. As we go along, I'll show you some tricks or some ways to know this, and I'll start with this one. Probably not worth your time or effort to memorize all the wavelengths and frequencies, but if you would do really well to memorize the wavelengths and frequencies of visible light. And that's because it's the most important part of the spectrum. It's right in the middle. So once you identify the start and end of the visible light spectrum, and they've expanded it down here. So once you recognize that visible light ranges from the red region down here, somewhere around that 750 nanometers or so, and all the way to the shorter wavelengths over here, somewhere around 350. So 2 easy numbers to remember is you go from 350 nanometers to 750 nanometers. And if you're curious about what a nanometer is, take a look on your data sheet, and it'll tell you it's times 10 to the minus 9. So the wavelengths of visible light range from 750 times 10 to the minus 9 meters to 350 times 10 to the minus 9 meters. I'm just going to highlight this page as well. This comes out of your textbook, and it just kind of goes into some detail. This will make a lot more sense later on, especially when you look at something like this method of production section here. But it gives you kind of an idea of the frequency of wavelengths of different parts of the electromagnetic spectrum. So again, you get this wavelength for visible light. They say somewhere between 400 and 750 nanometers, and that's a bit of an approximation. But as long as you know those kind of general start and end of visible light, you should be good to deduce the other parts of the electromagnetic spectrum. But I'll give you, just point this table out in your textbook, section 13.1. Take a look at it and just kind of become somewhat familiar. You're not going to have to memorize any of the points, but you should see some patterns in here in terms of when we learn a little bit about how we produce electromagnetic radiation and the different characteristics are interesting for you to know. Now, what we really want to come to some understanding about is this idea of what is electromagnetic radiation. And so there's really two competing models. One is the particle model, and the other was the wave model. Particle model visualizes light or electromagnetic radiation, but I mean, we talk about it now as a whole grouping of things because we recognize that every part of the electromagnetic spectrum is really the same phenomenon. But historically, people were talking about light and debating whether light is a particle or light is a wave. And there's lots of arguments that we could make for light being a particle that still hold true to this day, and lots that we can make that it is a wave. But ultimately, this debate that raged on a few hundred years ago was settled by one classic experiment. So, for kind of a summary of this experiment that kind of sealed the deal for the particle wave debate, I'm going to play just a couple of minutes from this YouTube video from Veritasium about the original, what we call double slit experiment. I encourage you to go Google search this and watch the whole thing. Very interesting, humorous video. But I'm going to watch, I'm going to play through just a couple minutes of this just to give you the historical perspective of the fascinating double slit experiment. All right. So, kind of get a sense of the experiment there, but let me take you through it in a little more detail. So, imagine that we take a light source over here. Let's say it's like a beam of light or a light bulb or something like this. And we shine this light source through what we call a double slit, which is really what it sounds like. Basically, this uh, barrier that you have that has two openings in it. So let me see if I can carefully draw this. All right, something like this. So we have a wall and there's two openings in the wall here and here. Um, and the light shines in all directions. So let me just change my color here. So imagine the light that's shining out in all directions. In the particle model, you would expect that light would shine, and in some cases it would hit this barrier and stop. It might shine in this direction, hit this barrier and stop. But there is a certain path that the light could travel on where it goes through the opening. And there's another one right here where it goes through the opening. And if you put a screen over here of some type, something to kind of see what's going on past the barrier, then you would expect to see two regions, each one kind of illuminated with this light. So you'd see light here and you'd see light here because the light shines through those gaps and shows up there. And then it would be dark in these other regions because the light's not reaching there. That's what you would expect for the particle model. On the other hand, if we asked ourselves what would light do if it was a wave, then you would have your light source over here again, emitting light in all directions. You'd have your double slit over here. And because light ripples out as a wave, you would see light travel in these circular waves, traveling from the source. And then at each of these openings, it would ripple out as well. And as it rippled out, you would get interactions with these different light sources. And so you can see certain regions where the light waves, if we think of the waves, crests are meeting crests here. Each of these lines could represent the crest of a wave. And then these dots that I'm indicating here, let's highlight them in like red. Each of these dots represents a place where a crest is meeting a crest, and those are moving outwards. And you would expect then at this point to get a bright spot. But you can also see there's locations here that we would expect to get bright spots. They ripple out and eventually they would hit the screen over here. And you get the same thing happening on this side. And when you do this with waves of water or any other waves, you get these regions where you get you get big waves at the red points. And then where I'm going to put X's, you get kind of like nothing. So if this was light, you'd get these regions of bright, dark, bright, dark. And this is exactly what happens. You don't get this particle argument going on. You end up getting these regions of bright spots. It's called an interference pattern. If you want to look into it, we'll talk about it a little more later on for sure. But it's called an interference pattern. And it only happens, as you can see from this argument, it only happens with waves. You wouldn't expect it to happen for a particle. So as we move forward in this chapter, we're going to be discussing this whole idea of light as a wave. So how do we visualize the electromagnetic spectrum as a wave? Well, most of the time we get a picture that looks something like this one, which you can find in most textbooks. It's hard to kind of see what's going on here, but in red, they have highlighted this magnetic field that changes here. So the electromagnetic spectrum really is the series of waves that are actually two waves simultaneously. One is a magnetic field wave that they've highlighted in red and kind of goes back and forth this way. And then 90 degrees to that, we have this other wave, which is this going in this other plane, and it's an electric field wave. So we have an electric field wave and a magnetic field wave. And so we picture, can't really see this happening with these waves, but we imagine and we picture these magnetic and electric fields moving 90 degrees to each other. Now, most textbooks show you this picture, so it's hard to really see what's going on or imagine what's going on. But here's an animation of what you might picture. So if you start over here, you get these oscillating or changing magnetic and electric fields, and they're always 90 degrees to each other. Think of your third left-hand rule. So as a magnetic field in blue changes one way, then decreases, then goes the other way, it creates an electric field, and that creates an electric field wave that ripples outwards. So you kind of have three things going on here. You get this changing magnetic field in one orientation, you get just changing electric field in the other orientation, and then rippling in a third orientation, we get this movement of the wave. So the wave is actually traveling this way, kind of to the right and out of the screen, if you think of it that way. So again, just like our hand rule has kind of one orientation, that is the magnetic field, maybe in and out of the page a little bit. And then we have another orientation, the up and down, or if you want to think of it as the Y, that's the vibrations or the changing electric field. And then finally, you have the direction that the wave actually travels in this direction. So all of these things 90 degrees to each other. If you think of it in math class, you got your X and Y. Here's my X, here's my Y. And then if we went in and out of the page, you'd get your Z. So we have this kind of sense or this idea that we have an experiment that tells us electromagnetic radiation, light, behaves like a wave. We have a theory here about how we can have this changing electric and magnetic fields. There was one person who kind of consolidated all these ideas, put it into one nice theory or series of predictions coinciding with a theory, and that was James Clerk Maxwell. And Maxwell came up with these predictions for the electromagnetic radiation. He said, if light and electromagnetic radiation really travels as a wave, then they are produced whenever an electrical charge is oscillating. Now, this is really important. We need an electrical charge, and it's got to be accelerating. Whenever you get this combination, electric charge plus acceleration, then you produce an electromagnetic wave. That's got to be the first and foremost. When that happens, the energy is radiated a wave and the electric charge loses energy. If we go back one slide here, if I can, the whole thing starts back here with some sort of accelerating charge. In this case, the charge might be moving back and forth to create these changing electric and magnetic fields. So Maxwell said electromagnetic waves are produced whenever I'm going to star this. That's because it's important. All right. Number 2, when the electric charge is accelerated in periodic motion, you'll remember this from earlier studies in physics, the frequency of the oscillation will correspond exactly to the frequency of the electromagnetic wave. So now if we go back and look at how we categorize electromagnetic radiation by wavelength and frequency, this is talking about the frequency. So Maxwell would say, if you take a charged particle and you oscillate it, you shake it up and down, just like you could shake up and down a string, then you will produce a wave that has the same frequency as the frequency that you oscillated. So if I move an electric charge up and down once every second, 1 hertz, I will produce a 1 hertz electromagnetic wave. So I'll know my frequency of that wave. Another contribution that Maxwell gave us, all electromagnetic waves will travel at the speed of 3 times 10 to the 8th meters per second. Now, this number is known as the speed of light. But if you're reading carefully and listening, it's not just light that travels this speed, it's every part of the electromagnetic spectrum. So by all rights, this shouldn't be called, although it will be, and you'll look on your data sheet, they'll call it the speed of light. We can extend that to the speed of all electromagnetic radiation. Got a little typo here. The other thing that this says is it obeys the universal wave equation. And that's the equation that says the speed is equal to the wavelength times the frequency. So no different than mechanical waves or any other waves, this formula works out. I'm going to put a star by number 3 because I think that one's very important as well. Number 4, the oscillating electric and magnetic fields will always be perpendicular to each other and perpendicular to the direction of the propagation of wave. And that's the argument I made on the previous slide where we had that image of the movement of this thing. Everything's 90 degrees to each other. Electric fields oscillate in one direction, magnetic fields in another, and then the wave travels in another direction, yet 90 degrees to that. The term propagation just refers to the fact that each wave or each changing field, magnetic and electric, produces another one. So once you produce the disturbance, it just moves on for itself, or it propagates itself is the term we use. Finally, electromagnetic waves should show all the phenomenon associated with transverse waves. And just some reminders, some of the things we'll study as well here. Interference and diffraction, refraction and polarization. These are all phenomenon that we're going to study in some detail in this course. So I'm going to stop there. This is supposed to be a brief introduction into electromagnetic radiation. Hopefully it was. Feel free to go back and look at it. Like I said, take a look. There's a few more details in your book you might want to take a look at. But we don't want to get bogged down in too much of this. It's the kind of thing that as we go through this unit, we'll revisit these ideas, keep coming back to the key ideas about Maxwell's theories, also talk about the ideas of light as a wave, electromagnetic radiation as a wave, and we'll get some practice with understanding or committing to memory some of these things we need to know about electromagnetic radiation, such as the order of the electromagnetic spectrum, the relative wavelengths and frequency. We'll get practice as we go, but we need to get on to bigger things. So I'm going to stop here. Not as brief as I'd hoped, but that's your introduction into light as an electromagnetic wave.